In this video, we are going to see what the second derivative has to tell us about the graph of a function. In particular, the second derivative is going to help us to identify how the function is concave. Right? So we're going to look at the concavity of a function. Now, to talk about the concavity, we first need to know, what do we even mean by concavity? Right? So let's define concavity. Let f be a differentiable function on an open interval I. The graph of f is said to be concave upwards on I when f prime is increasing. So when the derivative is increasing, when the slopes of tangent lines are getting larger, then we are concave up. On the other hand, we would say it's concave down on an interval when the slopes of the tangent lines, when f prime is decreasing on that interval. So when it's concave up, that's going to be curved upwards like a bowl, right? So that's concave up. Notice if we were to draw some tangent lines here, that tangent line is pretty negative. This next tangent line over, it's going to be negative but less negative, so that derivative, that slope, is getting larger, and it gets less negative. Maybe it hits 0, and then it starts to get positive and more positive. And so when we have those slopes that are increasing, it is concave up. Now that concave up, it can look like that bowl. It could be just like half of a bowl, right? So that is concave up, right? Or it could be the other half of the bowl. That's concave up. Those are concave up. Your slopes, as you move, slopes of tangent lines, as you move from left to right, they are getting larger and larger. Concave down, on the other hand, is curved down like a rainbow. So you might start with a very large positive slope, but then your slopes get smaller and smaller, eventually maybe hit 0, and then you start to get some negative slopes that get more and more negative, so our slopes continue to go down. That is concave down. And just like we had for concave up, you could have just half of that rainbow. Right? So it could be curved like that, or you could have the other half of the rainbow. So if you have horizontal asymptotes, you can see things like this. Yeah. All right, so that's what we have for concavity. That's what we mean by concave up and concave down. A graphical interpretation, let f be differentiable on an open interval. If the graph of f is concave up, then the graph lies above all of its tangent lines. And so if we were to turn back and we looked at those tangent lines that we drew on that first one where it was concave up, that graph is above the tangent lines, right? So it's concave up in those spots because our graph is actually above those tangent lines. And when it was concave down, it was below those tangent lines. Right? So that is a way that we could determine that graphically. And so if it's above all of its tangent lines, it's concave up. If it's below all of its tangent lines, it is concave down. Excellent. All right, so we have this idea of concavity. Now let's think about how we can use the second derivative to determine the concavity of a function. All right, so to determine if it's concave up, we said it's concave up if the first derivative is increasing. Now, when we looked at ideas of increasing in our last section, in our last sets of videos, we identified that a graph is increasing if its derivative is positive. And since the second derivative is just the derivative of the first derivative, then f prime is increasing when f double prime is positive. So if our second derivative is larger than 0, if it's positive, then our graph is going to be concave up. The original function f is concave up. And if our second derivative is negative, then the original graph of f is concave down. So to determine the intervals of concavity, we can look at the first derivative and then take from that the second derivative. Looking at that second derivative, if the second derivative is positive, it is concave up on that interval for all those values where it's positive. Everywhere where it's negative, our function is concave down. Now, you might notice that we did not identify what happens when that second derivative is 0. Well, part of the reason that we did not identify that is because we can have some strange things that happen at those points. So let's let f be a function that is continuous on an open interval, and let's let c be a point in the interval. If the graph of f has a tangent line at this point, c comma f of c, then this point is a point of inflection of f when the concavity changes from upward to downward or vice versa. So if our concavity is changing at a point from up to down or down to up, then we have an inflection point. So that's an inflection point, a point of inflection. Right, so c comma f of c is a point of inflection. So what that looks like in a graph is you might have something like this. Oh no. So maybe we have something like this. We have a graph that is concave down. It is concave down all the way up to roughly this point, right? So our tangent lines are above this. Right at that point, our tangent lines start to be below. This point right here is a point of inflection. Then we are concave down for a while. And then somewhere, maybe right about here, we're concave up for a while. So from here to here, we're concave up. At this point, we have another inflection point. Right there, it turns and it starts going down again. And we have one more inflection point right here. So from here to here, we're concave down. And then after this point, we are concave up again. So these 3 points that we've identified on this graph, those are points where it's changing concavity from concave down to concave up. Those are our points of concavity. Let's give these some numbers. If I call this 1 and 2 and 3, maybe this is 4 and 5 and 6. We could say that our graph is concave down on the interval from negative infinity up to 1, along with 3 to 5. And it is concave up on the intervals from 1 to 3, along with 5 to infinity. So that is the concavity of the graph. We had 3 different inflection points. Excellent. In our next video, we will look more at points of inflection. We will find those in an example. We will see you there.